Take this thing. I should just. Yes, we just translate. It is already translated. Right. It's good morning. But see, yeah, having Alright. So we are continuing from where we ended the other time. Already done a phase on the introduction to drives, what the types of drives, classification of drives. We also looked at the type of load, type of load torques. Yeah. And we saw how to find, we saw the equation of motion, right? The fact that E is equal to TL plus J d omega dt. All this here. We saw how to use it. We also saw that if there's a gear, if you have a motor here connected to a gear with another motor here, would have to refer to the motor shaft side. And we saw how to do that. So today we'll continue. Today we'll be looking at how to determine a certain parameter. Look at how determination of moment. That's the next thing. Determination of gravity. Okay. So determination of moment of inertia. Determination of moment of inertia. All right. So now here we'll look at three things under this. Okay. So let me go to the slides. So the moment of inertia is required to design a drive control system and to determine the transient performance. So it's usually determined experimentally because it's the rotating masses involved are complex and hence you can't like use mathematical calculations to solve them. So you'd have to determine it experimentally. So let's see an approximate way. Let's see an approximate way of determining the moment of it. Let's see the steps involved. Okay. So the steps involved is that first you have to disconnect all systems connected that are not contributing, all those systems, right? Then the next thing is that run the motor at above the rated speed. That's the second thing. Run the motor at a speed above the rated speed. Once you cut off the power source, just before you cut off the power source, you measure the power. You measure the power consumed by the motor. Now, when you cut off the power source, the motor will start to decelerate, right? So this power at that speed will now start to use. And this power will be converted into the kinetic energy that will transcend to zero. I getting it. So with this idea, we can say that okay, then it means that the power which corresponds to the rotational losses is what will be transferred or what will become rate of change of kinetic energy as the motor is reduced. So here's it here. So in order to determine our J, here's what we do. So let's try to plot a graph here. I have a graph of speed against time, right? Speed against time. If this is my rated speed here, omega r, so that run the motor at a speed above, let me call this omega 1. Run the motor to a speed above the rated speed. Measure the power. So let's call this power rotational losses. Rotational losses. All right. Now cut off the power source. You realize that as you cut off the power source, the speed will reducing with time. The speed reducing with time. So that's what happened. Okay, my brain is not. Let me read. Okay. We have a speed above rated speed. Have rated speed. Let me call this omega r here. And we say that okay, something like this. Speed reducing with time. Right. Now what you do is that you measure, you find the gradient of this curve at the rated speed. So here, you know that gradient, just draw a tangent, right? You find the gradient at that point. So you need to find the gradient. For this curve is dy, gradient is changing y by changing x. So this t. So the omega dt at the omega dt at omega r. Now, so you find the slope. Let me call it m. So you find the slope at this point. Now, you don't forget that we've also said that when the motor is reducing, when you cut off the power source and the motor speed is reduced, this rotational loss PR is given by what? The rate of change of kinetic energy. Rate of change kinetic. I hope it makes sense. Okay, sure. Now, this PR will be equal to D of K is what? Half J omega squared. Half J omega squared. Half J omega squared. So when I differentiate this with respect to E, the omega is a function of time. So I'll get PR to be equal to, this 2 comes to cancel this 2 out. So I'll just be left with J omega, J omega, J omega, omega dt. J omega, omega. Now, what are we finding? We are finding what? We are finding J, right? Yeah, so let's continue on those little h. So we are finding J. So we are finding J. Let's make J the survey. So I can say J is equal to PR over omega the omega dt, right? So J is equal to PR over omega the omega dt. So the omega dt at the rated speed, right? This is our omega r. So this is how we find our J. This is how we find our J. It means that if I have a function of omega, I have a function of the speed, I can differentiate it and put in the rated speed. I'll get the slope at that point. Now I know the rated speed. If I'm given the rotational losses, I should be able to find my J. Is I flowing? Yes, so that's it. That's how you come about it. That's how you come about it. Okay. Yeah. So you realize that usually you see because the rotational loss is acting opposite to the kinetic energy. Sometimes there's a negative here. Right? So you can have J is equal to negative PR. Except some places they don't bring it because the slope is negative. So it's like this negative will cancel this negative. In that case, yeah. But if you're taking this as a slope, then this is how the formula is supposed to appear as. Okay, so this is it here. Now, but except in this case here, you see, we just said that, oh, okay, run the motor above the rated speed, find the rotational losses, right? But then we didn't take into account the fact that there could be some losses in the system. Okay, so let's see what's in this slide. So yeah, so that's how we get J is equal to negative P over omega R, omega R T R. We have here. Now, let's find a more accurate way of determining J. A more accurate way of determining J. In this case, we have to consider the fact that there could be some electrical losses in the system. What we do is that what you do here. So please take note of this first part. We'll take a numerical example. So let's see a more accurate way. A more accurate way is to do this. Is to now run the motor at different speeds. You see, in the first case, we just run the motor at a speed above the rated speed, and then allow it to go off, and then you measure the rate at which the speed is decreasing. Okay. In this case, now here you'd have to run the motor at different speeds, and then measure the rotational losses at those speeds. Okay, so that's what is different. What's different is that you obtain rotational loss for the drive under steady states at various speeds. So once you have the rotational losses, which is PR. Okay, we know that our power is what? Power is what? Torque times what? Speed. I can write my PR as torque. What is TL is like rotational loss torque. And this is my omega R. Right. So if I find the rotational losses and I divide by omega R, the rated speed, then I'll get TLS. So I can now plot a graph of what? Look at that. This part will give me the graph of the. From here, I can find my d omega dt, right, at the rated speed, omega R. Now I can also plot a graph of TLS, torque against omega. I said I can also plot a graph of torque against speed. A graph of torque against speed. So here, this will correspond to my torque, rotational loss torque against speed. And that graph will look something like this. It looks something like this. Yeah. So now I can have the formula, right? I know that in the first case I had J was equal to what? Minus PR over omega d omega dt, right? But I know that I know that PR over omega is TLS. So I can say J is equal to what? Minus rotational torque losses over the omega d. So this is another way we can compute J. When we take a numerical example, we will see how this is actually used. We'll see how this is actually used. Let's move on. Now, finally, another way we can compute our J. Another way we can compute our J is, now we know that what? We know that, let's say, P, the rotational losses, right, is some function of omega. Is some function of omega, right? Rotational loss against speed here. You know that speed is a function of time, right? So let me call this G of t here. Now, if I'm able to find omega as a function of time here and put this omega here to compute my power, then I can now get a graph of power against time. This should make sense. P, the rotational loss is a function of omega, speed. Speed is a function of time. So I can do something like back substitution, where I can now come and get rotational loss as a function of time. So I can now plot a function of the rotational loss, let me call this P, against time. This is a time axis. And that will look something like this. So this corresponds to a function of rotational losses, which is P, against time. Against time. Now we know that what? We know that power is what? Power is energy over time, right? Working over time. So power is energy. Energy over time. Energy is what? Power times time. So this graph of P against time here, the area under this, the area, which means we know that area is what? The integral, right? So integrating this function of time, dt, the area under this curve corresponds to what? The kinetic energy. So this area will correspond to kinetic energy. So all we are seeing is that I can have I can give a power, a rotational loss power as a function of time, right? And the area under that P against T curve will correspond to kinetic energy. So we know that this area and kinetic energy is what? Half J omega naught squared, right? Half J omega squared. So from here I can say, okay, this implies that my J is equal to what? 2A over omega naught squared. So this is another way that we can find our J. This is another way we can compute our J. When we take numerical examples, we'll see all what these mean. So let me just briefly talk about what we've done so far. So we are saying that if I'm giving a function of speed against time, right? Speed against time like this, then I find my J what? Minus PR over omega, then the gradient at that point, the gradient at the rated speed. That's at this point here. Yes, this is number one. Now, number two is a more accurate way. That one, we consider the fact that there are electrical losses. So in that case, I'll plot a graph of torque against speed here too. And once I have my graph of torque against speed, and I'll be able to compute my gradient at this point here, then my J will be equal to minus DLS over, because this over this will give me the torque, over the omega at omega r. Now finally, if I'm able to plot a graph of power, rotational loss power, against time, then the area under that curve will correspond to my kinetic energy. Therefore, my J will be equal to 2A over omega naught squared. So these are the three things I'm supposed to know. Here, here, and here. When we take numerical examples, these things would make sense to us. So let's see. So let's take an example. Okay. If I forgot to mention, the name of this test is called the retardation test. Don't forget that we run the motor and then we allow it to decelerate. That's retardation, right? So yes, so it's called a retardation test. Let me clean this here. So in the example here, it said that in a retardation test, the speed of the motor at a time t seconds after the supply has been cut off is given by omega is equal to 100 over 1 plus. If the rotational loss, so we've been given rotational loss as a function of speed as a function of time. Don't forget that we said that if I'm able to get rotational loss as a function of time, then the area under the curve will correspond to my kinetic energy. So let me substitute. I've been given P to be equal to what? P is 0.02 omega squared. Omega is 100 over 1 plus t. Omega is 100 over, you know. Okay. So let me put equation 2 into equation. So put 2 in 1, right? When I put 2 in 1, I'll get P to be equal to 0.02 times omega. Omega is what? 100 over 1 plus t squared. So P will be equal to 0.02 times 100 squared all over 1 plus t all squared. So punch 100 squared times 0.02, 200. So I'll get P is equal to 200 over 1 plus t. Now this is a function of what? P against time. It's a function of P against time, right? And we said that if I'm able to find a function of p against time, then the area under this function, will give me the kinetic energy. So the area under a function is the integral, right? So I'm having this function here. And I'm supposed to integrate it. So the integral of p, right, from 0 to infinity, and p is what? P is 200 over 1 plus t all squared. The integral of this, which gives us the area under this curve, should be equal to kinetic energy. So first, let's find the area under this curve here. So this is integration, right? From 0 to infinity, I can bring 200 here. Have 1 over 1 plus t all squared. 1 plus t all squared. Okay. So now I have 200 here, right? Then this will give me, I got this become 1 plus t minus 2. So I'm having what? Add 1 here, right? And we divide. So I'll be left with negative 1 over 1 plus t. I'm left with minus 200. 1 over 1 plus t from 0 to infinity. When I put in the upper limit, here, I'll get minus 200 times 1 over 1 plus infinity. That will give me 0. Then minus, when I put in lower limit, I'll get minus 200 times, when I put in 0 here, I'll get 1. So the answer is minus 200. That's giving me a positive 200. So this is the area. So this is the area here. The area is 200. And we are saying that this area is equal to kinetic energy, which means that area, which is 200, is equal to what? Half j omega naught squared. So j is 2 times 200 over omega naught squared. Let's find what omega naught is. Omega naught is the initial speed. So we're given the speed function to be what? 100 over 1 plus t. Initial, it means when time is 0. So when time is 0, the speed is what? 100 over 1. That's 100. So this implies that j is equal to 2 times 200 over 100 squared. 2 times 200 over 100 squared. So that's what? 400 over this 0.04 kilogram meters squared. Please take note of the unit. Kilogram meter squared. Kilogram meter squared. Kilogram meter squared. Kindly hold on. Okay. So that's it. So that's it for that question. That's it for that question. Yeah. So we've seen how we use the formulas, right? Now let's move on. Move on to the next here. Okay, let's move on. Next question, right? Now it says that the rotational losses of a motor are given by the rotational losses of a motor are given by 0.02 omega squared. So we've been given PL to be equal to 0.02 omega squared. Estimate the moment of inertia if the retardation test on the motor yields the data tabulated below. So here you can see that this is like we can take it as in the second case, right? We can take this as in the second case. Or let's say we said that J is equal to minus EL over omega. This is the slope of the curve. This is the speed. This is the PL, which is given here. And we know that PL over omega gives us what? PL over omega gives us TLS, the loss torque. So TLS over omega T. TLS over the omega T. TLS over the omega dt. So this is what we use. So if you check in the question, we've been given the slope. That's the omega dt here, right? We've been given the speed, omega. So let's see. We know that TLS is what? TLS is PL over omega, right? PL is what? 0.02 omega squared. So if I divide it by omega, it means my TLS is 0.02 omega. It means that my J is equal to negative 0.02 omega over omega d. And this is what I'll use for all the times. So first I'll take when time is 1. So in the first case, when time is 1. So at t is 1, J is equal to what? Negative 0.02. The speed is 50. Speed is 50 in the question. Speed is 50 here. The slope is negative 25. So negative 25 like this. So that's how you go about it. So you simplify this, you get your J. So kindly take your time to punch it. So you get 0.04 kilogram meter squared. Now when t is equal to 4, the second case, I get J is what? Oh, I get J is equal to negative 0.02 times, in that case, the speed is what? 20. Slope is negative 4. So times 20 over negative 4. Go here, 5 to 10. So I get 0.01 kilogram meter squared. 0.1 kilogram meter squared, sorry. I get 0.1 kilogram meter squared. So here J is 0.04 kilogram meter squared. Here J is 0.1 kilogram meter squared. Now finally, when t is equal to 9, speed is 10, slope is negative 1. When speed is 9, J is equal to negative 0.02 times 10 over negative 1. That'll give me what? 0.2 kilogram meter squared. So now we have J, right? We have J at different times. So if you want to find the J, you want to find what J actually is, you just find the average of all these three. Find the average of the three. So average is just the sum. So average is the sum. 0.04 plus 0.1 plus 0.2. And there are three J's. So all over 3. When you multiply this, you get 0.113 kilogram meter squared. 0.113 kilogram meter squared. So there we have it. Yes. So that's it. So you are seeing how we use the formulas, right? In the retardation test, you are seeing how the formulas are used. Okay. Now let's look at the next thing, steady state. We'll try more. Rob mentioned some questions that he has given us, so I'll take them from the TA and we'll try them. So we'll meet some of these questions under them. The next thing is the criteria for steady state. Criteria for steady state. So we said that the equation of motion is what? TE equals to TL plus J omega dt. Let me bring TL here. TE minus TL is equal to J omega. Right now, in a case where when E is equal to TL, it means this difference will give me 0. 0 is equal to J d omega dt. I can say d omega dt equal to 0. So when TE is equal to TL, as we can see here, when TE is equal to TL, you can see that the rate of change of velocity is 0, right? Meaning that the body remains in steady state or remains constant. So I can write that a steady state, TE is equal to TL. Don't forget that we said that TE can depend, TE depends on the speed. So TE as a function of the speed is equal to TL as a function of the speed. TE as a function of speed is equal to TL as a function of speed. What this means that if I'm able to plot a graph, right, a graph of TE against omega, say this, and I have another graph of TL against omega, let me say this, right, the point where they intersect, that's where they are equal. That point is what will give me the steady state value. Pause. Okay. Hello. Okay. So yeah, so with the steady state, a steady state, E is equal to TL. So if I have a function of TE, a function of TE in omega, I have another function TL in terms of omega, I can equate both of them and find the steady state operating point. The steady state. Okay. So now, once I'm able to find the steady state value, the next thing is to determine if that operating point is a stable point or not. So first thing that they can ask is to find the steady state point, the steady state operating point, steady state operating point. Which we said that at the steady state, E, a function of omega, plus L, a function of omega. Now let's define if the operating point is stable or not. For the operating point to be stable, you check, you find ETL omega, and you find ETE. So you differentiate L with respect to omega and differentiate TE with respect to omega. So this is stable when if the L is greater than TE here, then the function is stable. So this T at the rated speed or at the steady state speed, let me call it at omega naught. At omega is equal to omega naught. So this steady state operating points, you find the omega to be omega naught, right? So stable is stable when the L d omega is greater than the T d omega at the operating point. 2 is unstable. It's unstable when what? It's unstable when the TL d omega is less than the T omega at the operating point. Finally, it has neutral stability. It means in the middle, it can almost toggle between with the slightest disturbance to go to stable or unstable. Right? And that one, L d omega is equal to omega. So these are the three possible conditions that we can have. Either is stable, unstable, or neutrally stable, neutral stability. So these are the three possible conditions that we can have. Now, let's take a graph like this. Let's see how we can even think of this just using graphs. If I have a graph like this, and I have another graph at this point, and I say this graph here, this one on top is TE, and this one coming down here is TL. The one going up is TE, the one coming down is TL. Already you can tell that the slope of this curve here is a positive slope, right? So DTE is positive, DTE d omega is positive. DTL d omega, the slope of TL, which is DTL d omega, is negative. So that means that DTE is bigger than DTL. So for such a graph like this, it's unstable. So that's how we interpret those graphs that way that are in the slide. If I have a similar graph like this, and I have one going up, one coming down, and I say this is TL, this is TE. The one going up has positive slope. It means DTL d omega is positive. DTE d omega coming down is negative. So once this is plus any number is greater than negative of any number. So that means that this condition is satisfied, hence making it stable. Okay. Now for neutral stability, that one is a bit difficult to draw, but let me draw it. For neutral stability, the gradient at the point we are talking about, neutral stability, that one looks something like this. Say it is the first one here. Second one is something like this. Sorry. Right. So that one, they touch at more than one point, like they touch at a number of points. So neutral stability, it doesn't have one operating point. So note that in neutral stability, there is more than one operating point. In neutral stability, there is more than one operating point. There is more than one operating point. That's one. So that one you can see that yes, the gradients will be equal, but it's overlapping. Overlapping, they're going to be equal. Okay. Okay, so that's it. Right, let's move on. Okay, so let's end here for now. No, let's take an example. Take an example here. We take this example, and then we would end. Okay. Explain this one before we continue the next time, but I want to do this example since it will just help us solve what we've learned right now. Okay, so let's move on. Okay, the torque speed curve of a motor can be described. We've been given T as 2 plus 0.1 omega. T is equal to 2 plus 0.1 omega. Now for a range, okay, so this T is from 0 to 6. So from 0 to 6, from 0 to 6 inclusive. This is a electric torque. Then now from 60 to 100 is 20 minus 0.2 omega. 20 minus 0.2 omega. That's from 60 to 100. And we've been given TL. The motor drives a constant load torque whose torque is 6. So TL is given by 6 Newton meter here. Now, first question says that can the motor start together with the load? Now, let's see. TE is equal to TL plus J d omega dt, right? TE minus TL is equal to J omega dt here. So if TE is bigger than TL, it means I'll have a positive value here. And that means that the omega dt is a positive number. It means it's accelerating. So for the motor to start, for the motor to be able to start and accelerate, TE must be bigger than TL so that I can have a positive number here. So at starting at, so let's check at omega is equal to 0. Let's find TE at, so when omega is 0, that one corresponds to this point here. So TE will be equal to 2 plus 0.1 times 0. That's 2. So at starting, which is at omega is equal to 0, which is at starting, TE is 2. And we know TL is constant, TL is 6. So at starting, you can see that TE is less than TL. This is 2, this is 6. But we said for it to be able to start, TE must be bigger than TL. But here it is not so. So that's it can't start. They can't start together because TE less than TL. That's what we found here. Here. And the second question says that find the two possible steady state values. Now we say that at the steady state, so just write at steady state, it here, TE equals to TL. And we have two functions of T, so I will equate them individually. So let me take for the first case. TE is 2 plus 0.1 omega must be equal to TL 6. So 0.1 omega is equal to 6 minus 2, 4. Omega is equal to 40 rad per second. Also, the next one is this 20 minus 0.2 should be equal to 6. So you equate T to TL. So I'm still referring this to here. So here I'll get 20 minus 6 minus 20, that's negative 14. 6 minus 20, that's negative 14. Omega is negative 14 over negative 0. That's giving me 70 rad per second. So I'm getting 1 omega with 40 rad per second. And also the second omega is 70 rad per second. So that's it. So if you want to find the steady state operating point or the speed, it's just by equating TL. This is TE here. So I'll equate this one to TL, find the speed, equate this to TL, and find the speed at that point. So that's it. 40 and 70. Now the last question is that which of the two speeds is stable? Which of them is stable? Let's see. We know, and we say that for stability, yeah, For stability, we say that the TL omega should be greater than TE omega at the steady state speed. So let me find the TL the omega. The TL is a constant. TL was constant, it's 6. If you differentiate constant, you get 0. So the TL the omega is 0. Is 0. Now for the first case, let me find the T the omega. The T the omega for the first one. The T the omega here is 0.1. Is 0.1. And here 0.1 is bigger than 0, which means that DTL is smaller than DTE. So the first one corresponds when the speed is 40. So when the speed is 40, operating point is unstable. Operating point is unstable. That's the first case. Now let me take it in the second case. DTE, DTL is always a constant, so that'll give me 0. Let me find DTE, the omega in the second case. That'll give me what? Minus 0.2. So in the second case, DTE, the omega is minus 0.2, which is less than 0. So here, DTL, the omega is greater than DTE, the omega, which implies that at omega is equal to 70, operating point is stable. Operating point is stable. And that's how we'll go about this question. And that will be it for this stream. We'll continue again. We'll catch up. Okay. I'm sorry for all the times that we missed. We'll catch up. Thank you.